The living brain is a dynamic environment. Neural tissue is in constant motion, shifting and pulsing with every heartbeat and respiration. When we learn a new skill, the brain decides what to change cell by cell. Recent research from MIT demonstrates that individual dendrites receive precisely targeted, vectorized instructive signals. These localized instructions function exactly like backpropagation in artificial neural networks. The brain computes an error signal and uses it to fine-tune the connections of specific neurons. For neuroscientists, detecting these exact error calculations has been a persistent physical challenge. Until now, mapping the activity of a single neuron to a specific behavioral outcome was an unsolved variable. To intercept this targeted data, interface hardware requires high-density spatial resolution, capable of isolating signals at the single neuron level across thousands of potential sites. Historically, learning was thought to be governed by broad chemical baths, like the release of dopamine across large groups of neurons. Because all synapses receive the same signal in a chemical wash, tracking broad neuromodulators cannot decode precise biological learning. The required bioelectronics must spatially map individual dendritic error signals without disrupting the living tissue itself. Building that interface exposes a severe engineering bottleneck. We face a direct compromise between structural precision and biological compliance. Legacy hardware splits into two primary pathways: rigid silicon and flexible wire. Silicon shanks offer a fixed, highly precise array geometry. Their prefabricated sites allow for inherently low impedance, which minimizes thermal noise and yields a clear recording. But silicon's rigidity introduces a catastrophic biological drawback. It resists the natural movement of the brain, causing tissue dimpling and cumulative damage to the soft, pulsing tissue over time. Wire bundles offer an alternative. They are malleable and move with the anatomy, but their insulation wears away. Furthermore, increasing the channel count requires increasing the overall diameter of the device. Bypassing this binary choice requires a different engineering approach: a liquid metal elastomer plasticizer composite. Capturing vectorized neural signals at high density demands the electrical conductivity of a metal, perfectly matched to the extreme mechanical compliance of living tissue. The foundation of this composite is a styrene, isoprene, styrene, or SIS, block copolymer. Unlike conventional polymers, SIS relies on physical crosslinks rather than covalent bonds. To process this solid matrix, the SIS pellets are first dissolved in a toluene solvent. Next, polybutadiene, or PBD, is added as a plasticizer. This lowers the matrix's tensile modulus, bringing its mechanical properties in line with soft biological tissue. The conductive element is introduced via an emulsion process. A eutectic alloy of gallium and indium is mixed directly into the polymer solution. High shear mixing breaks the liquid metal down into a precise microscale geometry, forming discrete droplets that average 27.8 microns in diameter. The solution is cast into sheets and solidified in a convection oven at 80 degrees Celsius to remove the toluene and stabilize the suspension. In their resting state, these droplets remain physically separated and electrically insulated from one another. The raw composite is a complete insulator. This uniform dispersion provides a pristine base material, ready for the on-demand creation of electronic circuitry. Conductive traces are written into this material through a process called selective percolation. A mechanical testing machine applies a compressive load through a 3D printed mold, driving plastic deformation into the local matrix. Under this load, the dispersed liquid metal droplets rupture their insulating oxide skins and percolate, forming a connected, conductive micronetwork. This plot shows resistance measured in real time during the compression process. The feedback loop halts the applied load the exact moment the target conductivity is reached. Standard metallic physics dictate that when a wire is stretched, its resistance increases exponentially, governed by the square of the stretch ratio. This chart shows the predicted resistance spike of a standard metallic conductor in red, contrasted against the actual measured performance of the embossed liquid metal composite in blue. The data shows that the composite's conductivity maintains a nearly constant, highly functional state, reaching 45,400 Siemens per centimeter, even at 1,200% strain. These photographs show an integrated LED circuit operating flawlessly on the embossed substrate while subjected to 0, 120, and 240% active strain. This flat resistance profile proves that the fluid micronetwork within the composite actively reconfigures its internal connections to maintain conductivity, regardless of extreme physical elongation. Soft electronics designed for rugged biological environments must survive thousands of cyclic deformations without electrical failure. This graph shows the cyclic testing results. Across 1,000 continuous tensile cycles at 100% strain, the ratio of instantaneous to initial resistance remains highly stable. To evaluate dynamic self-healing, the composite was subjected to a rigorous hole-punch stress test under active mechanical load. This chart shows the applied strain profile over time, paired with photographs showing the physical state of the dog bone sample, as 4 consecutive holes are punched directly through the conductive trace. Despite the physical removal of significant portions of the material along the functional line, electrical conductivity is seamlessly sustained. The measured resistance actually drops slightly after each severe damage event. The liquid metal network instantaneously reconfigures, forming new particle-to-particle connections around the rupture site. In conventional solid metallic films, microscopic fractures under strain cause immediate and catastrophic circuit failure. This fluid micronetwork addresses the core mechanical challenge of chronic implants. It provides a stable electrical path that maintains connection even as surrounding tissue shifts, swells, or undergoes significant physical stress. Because the styrene-isoprene-styrene matrix relies on physical crosslinks, the composite allows for non-destructive circuit reconfiguration. These photographs show targeted circuit erasure. Applying toluene solvent locally breaks the liquid metal network, opening the circuit and turning off the LED. Once erased, a completely new conductive trace can be embossed immediately over the targeted region to reroute functionality without replacing the hardware. At the end of the device's life, the entire composite can be dissolved back into toluene and subjected to high-shear mixing, completely restoring the original homogeneous emulsion. This chart shows the stress-strain behavior of pristine composites compared to first- and second-generation recycled samples. The recycled materials successfully reach 1,000% strain, with mechanical properties matching the original. The result is a reprocessable substrate that combines the low thermal noise of pure metal with the physical compliance of biological tissue. By solving the mechanical mismatch with selectively percolated liquid metal composites, we have engineered the hardware foundation required to interface directly with the brain's precise vector.